Hi, my name is Karim Malkin. I'm CTO of Starboard Storage Systems. And I'm just going to take you. Say it again.
And this is your baby.
And this is my baby. You're absolutely right, Howard. This is my baby. So the folks before me covered the basic ideas that went in behind this technology. But really, what this was all about is how do we make a storage system that's easy to use and it's easy to scale, and that would be not a pain to manage day to day. All right, and it's also not going to be as expensive. And this is where essentially we came up with the basic ideas for that. Single pool of storage where we can always add the disk, whether it's on the same chassis or we have to throw in another JBOD or more. We always can just keep adding storage to that and eliminate any kind of a headache that has to do with thinking about what the stripe size is, how many disks are supposed to be there, how many disks are supposed to add. It should be possible to just add disks one by one or entire shelf or multiple 45 drive JBODs, if you will. That's number one. So that's for capacity, to remove that pain. The other point is how do we make sure that the performance is, it's possible for the user to control performance, meaning that if I'm out of performance, what do I need to do to fix that? And this is a frequent call kind of a, okay, my performance is not good. What do I do to improve it? Well, we answer that question by adding what we call SSD acceleration tier that can be always expanded with enough SSD capacity to grow the performance adequately. And then finally, the important thing is, how do we bring all workloads on one storage system? Because quite frankly, it's easier to manage one system than multiple. And then it becomes a question of consolidation, and the consolidation is always a question of proper sharing. And this is where the cache or SSD resource essentially comes in, as well as memory cache, as well as CPU, and how do we manage to share it fairly across the applications. Next slide. So let me just take you through the basics. Essentially, we start with the raw disks. They could be any size, essentially, and they can spin at any given speed. We slice them into smaller, manageable extents, and then we organize them into what we call layouts. And layout is essentially a source of data stripes. It's a virtual source of data stripes. It's not concerned which disks it's coming from. It's just concerned of how many independent disks are in the stripe, what's the protection scheme, and what kind of a sparing we're using. And I'm going to get into that a little more. And then we take the stripes and we organize them into virtual volumes. And it's just as simple as that. It's a very simple idea, really, but that's what Dynamic Pool is all about. Next slide. Then the next step is the acceleration. So obviously, hard disks are slow. No matter how many we add, I mean, they're still slow. So we fix that by accelerating the I/O using the SSD. So we do that separately for writes and reads. And as far as the writes are concerned, we are using mirrored SSD pairs because we're going to have to end up with I/O sitting on that single mirror at some point. And we try to look at our I/O stream, and we try to separate small, inconvenient little I/O that really hard disks don't like, and try to send it to the SSD, and then take the large wholesale kind of I/O streams and send them directly to the hard disk. What that does for us, it saves, to some degree, it protects the SSD, right? It doesn't overburden the SSD with the data that it doesn't need to hold. And at the same time, it doesn't impact the performance of the hard disks. So finding the right balance is really what the right caching is all about in Starboard. Then, of course, this cache could be fairly large. I mean, typical solution would be to install an NVRAM, which is 2, 4, 8, 16 gigabytes. We're installing 200, 400 gigabyte mirrored pairs that allow us to really hold that data for a long time until we feel like we're comfortable to flush that into the hard disk pool. When do we feel comfortable about it? Well, when they sort of organize themselves into longer stripes or longer segments that we can now, again, kind of a wholesale flush to the hard disk pool.
Which process do you use to flush? What sort of policies do you use to flush?
Well, essentially, that's a great question. So there's multiple policies that go in. First of all, we analyze how much data we can coalesce. In other words, how we can build a large enough segment of data so that we can flush it in one shot. Remember, the hard disks like large I/O, long I/O. This is why we're trying to organize that. Now, the fact that we have so much more write cache allows us to do that. We can hold the data in that cache for days if we have to, right? Until it organizes itself, hopefully, into a larger stripe. We also trickle flush that, right? And then we also look at how busy the disks are in the pool. So we're trying to parallelize the flush process. Remember, we have so many disks. We can expand to a fairly large pool, so we can parallelize the process of flushing. So that there's several optimization schemes that go into that policy. So also the mirrored SSD pair also handles the metadata. I'm going to get into a little bit more about the metadata. It's not really heavy, and the only reason we actually maintain the metadata mostly in memory, in DRAM, and we only journal them to the SSD. So it's not really a heavy use of the SSD for the metadata. Now let me get into Read Accelerator for a moment. What that is essentially a capacity, additional capacity that magnifies our DRAM cache. It's obvious to hold some data in the DRAM when it's been read, for example, or keeps being read. We hold that data in the cache for a while. The next thing we can do is we can compress that data and keep holding it if it's not frequently accessed. The next thing after that, what we do, we would sort of spill it over into the SSD that sits on the side, and just gonna, instead of just dumping it completely, we'll sit there, and in case there's another cache miss, then we'll go into SSD and bring it back into the memory, right? So, and then we're very careful about how we maintain, because it's a huge cache, really. I mean, if the write accelerators are 200, 400 gigabytes, then the read accelerators could go up all the way up to 6 terabytes. So that's a huge cache, and if it's compressed, you're talking about gazillion, literally close to a billion stripes that we can potentially hold in that accelerator. What that does for us, it makes the system essentially flash mostly. For the purposes of the workloads that look at that system. And then we take the benefit of that for performance, and then we take the benefit of cheap capacity, which is hard disks, for storing large amounts of data. And then it becomes the equation of how much capacity versus how much cache. Next slide. Go ahead.
Go ahead. I'm sorry, but what about the IO blender effect that you can see?
That's a great question. That's a great question, because that's exactly what Write Accelerator allows us to absorb. We're separating, remember I mentioned in the beginning that we're separating small random writes from large sequential. That's what eliminates or solves the problem of IO blender. Because the blender is when you get a little write and then you get a big write, then you get another read, okay, and it's all extremely inconvenient because then it plays with the mechanical latencies of the hard drives, and it really becomes a problem. If you put the SSD in front of it and you just filter the small I/O, small random I/O, that SSD is really can keep very well with, okay, and then you send larger I/O into what I call linearized disk pool. I'm going to get into linearization a little more. Then you essentially solve the blender, or at least I would say you significantly improve the negative effects of that.
So you can decide how to store single blocks from a single server, from each server of the cluster.
Well, the system decides that, right? So one important point of this architecture was to try to eliminate any kind of user interaction, so that the user said, "Oh, I have to pin this volume to the SSD." No, we don't do that. We let the system make that decision just in time. When when the latency essentially grows for a particular host, what we're trying to do is we're trying to fix that by appropriately sending the data to the faster performing tier.
But when does the host get the acknowledge? When it hits the SSD or
the acknowledgement gets when the data is stored either on the SSD pair, in other words, it's either stored on the mirror or it's stored in the pool, depending on where it goes. So if it goes in the pool, then you get the acknowledgement once the data is stored in the pool and the metadata pointer has been switched.
Okay. And isn't there a risk to see different latencies, because the algorithm need to analyze the traffic before deciding what to do? So you have increasing latency for some time, then you decide to move the blocks on
well,
other tires.
the great the great benefit of the architecture that we have is that it's based on x86. That's essentially the fastest architecture in the world, whether we like it or not. But that is the fastest architecture, and it's also multi-threaded. So we get the benefit of enormous DRAM capacity, and all that decision is made, really the decision-making process is very simplified. And the fact that we have this high-performing CPU and so much memory where we can store enough supporting data to make that decision really quick. And I'm going to get into that in a second, because if you, let's go to the next slide. So let's talk a little bit about what we do in terms of building this dynamic pool, and how we use the benefit of large memory to optimize and actually, quite frankly, simplify searches that need to be done when, every time you do virtualization, you have to, bounce off some kind of a search. So we're trying to optimize by keeping searches linear. There's like multiple steps involved in operating of the dynamic pool. The first step is physical storage abstraction. So what we do is we take all the drives that the customer may have inserted for us, or we actually inserted for the customer, and whether they are in the head unit or they're in JBOD, there's really no difference. We look at them the same way, and we group them by their characteristics, mostly by the speed and type of attachment. We could potentially also handle external array LUNs. Not in this product, but it's possible. There's nothing wrong with just connecting external LUNs as well. What we do is we break them into extents, as I mentioned, and they're relatively large. What that does for us, it creates microdisks, essentially. Out of every disk, it creates, like let's say it's a 1 terabyte disk, so it creates 1,000 microdisks. We further break the extents into fixed size chunks. And the chunk is the minimal addressable capacity increment. And that could be anywhere from 16K to 512 kilobytes. What we do with that is we take these chunks and we think of them as a stripe, okay? But we really, because the chunks are sitting on extent, we're building a sheet out of multiple extents. And each extent in the sheet is really either data or parity or a spare. Next slide. So you can see it, pretty much right here. So we take the extents, we break them up in chunks, and then we coalesce them into a stripe. And stripe is a minimal unit of allocation in this dynamic pool, right? So we have data, any kind of a number of data stripes, parity, potentially, dual parity, and also spare chunks that are also embedded into the stripe, so that I'm going to get into that a little more. It's going to facilitate rebuilds a lot better than traditional methodology. So you can also probably glean from this is that it pretty much doesn't matter what protection scheme you're using. You can be using single parity, you can be using a mirror if you wanted to, you can be using dual parity, you can be using any kind of erasure schemes, you can even use non-erasure schemes if you wanted to.
But today you support mirroring and
today we support mirroring and single parity.
You don't support double parity?
Not today.
Are you doing CRCs or hashes or other kind of chunk integrity?
On the metadata, yes. We're also doing scrubbing. We're doing scrubbing and just-in-time correction as well. So the second.
The effect of a dual drive failure on a single parity scenario that we implement is very different than it might be in a typical RAID 5 group, for example, because of the way the data is laid out across the drives. And I'll let Karel get to that a little bit too.
There's also a spare chunk as well.
Yeah.
So
that helps a lot.
Every stripe.
Next slide, please. So when we go to the second step of this process is to create virtual volumes. And the reason there are two steps is because you can probably guess that that extents are linearly mapped. So there's what we call sheet map, which quickly gets us to the right extent on all the hard disks. And the second step would be to see where the stripes are on each virtual volume. So volumes themselves are also broken into fixed size stripes, and each stripe is essentially either mapped or not mapped to a particular stripe inside the dynamic pool. It's just that simple. Only mapped stripes point to the physical storage. If they're unmapped, if they're containing zeros or something like that, they're not pointing anywhere, and the system knows about it and can produce data real quick. that's the best way to get iometer to show like 400,000 IOPS is just you know try to feed it 0 stripes, but you know it looks real because it's volume, and you know you can do it.
Not the version of iometer I
Yeah, well, depends if you're reading or writing, right? So step 3 is transactional updates. So this is a very important design decision for this architecture, and this is a sort of a non-typical for dynamic pool type of designs. New reads are always redirected new writes, are always redirected to pre-allocated stripes. So what that means essentially is we're building a new stripe every time we write, to the pool, I should say. So what that does is, on one hand, it simplifies the management of this system immensely, because all of a sudden we can part with NVRAM, we can part with batteries, we don't have to worry about incompletely written stripe. We only switch the pointer to the new data when the data write is complete, meaning that the parity has been calculated and written out, and all the data chunks are written out. So we can never have a situation where the data is partially written and therefore corrupted. The negative part of that is that of course, there are missing parts that you need to still read. So it introduces read, modify, write cycle to some extent on some workloads. But what's interesting is, because remember, this dynamic storage pool sits right below the SSD tier. And the SSD essentially makes sure that we can create larger writes to the hard disk pool, as we discussed. And that's what mitigates this problem tremendously. That essentially eliminates read, modify, write cycles for the pool. And the second thing is kind of to your question is, you know, advanced I/O stream analysis. So we do analyze the blocks as they come in, requests as they come in, on whether, you know, this is a small random I/O. I mean, where does it go? How busy is the pool at the moment? And we try to redirect smaller writes to the SSD. That is the write-back accelerator, and that SSD is certainly mirrored. It retains it. You know, we can safely commit to the application when we're written to the SSD, and then eventually the background task is going to copy this out to the hard disk. We are trying our best to get the larger writes and streams. We're obviously running multiple levels of stream detection there, and send it into hard disks into the pool and try to bypass the SSD so that it's better suited for random I/O. So this illustrates what we just discussed a little bit better. Just a picture from the volume perspective, which means from the host perspective, that you know, from one of the LUNs or potentially a file system. All the writes are separated into small random and large sequential. The small random is hitting the SSD mirror. The large sequential is going into what we call stripe cache, and eventually they end up in the dynamic storage pool. Dynamic storage pool provides redundancy and healing, whereas when the reads are happening, most of the reads are coming from the stripe cache, or so we hope. Some reads could still come directly from the write-back accelerator, because there's a considerable amount of data already there. So if the read comes in, then we'll go back to the write-back accelerator and read it from there. The reason that arrow is thin is because we certainly hope that the application, or I must say file system, whether it's NTFS or VMFS or somebody else, they will not read the data that they just written, you know, because they have their own cache. So we're cognizant of that, but it's still possible to see some of that reads, especially on tests. So also what happens in the read path, we maintain the stripe cache, which contains a certain amount of uncompressed stripes, because we need uncompressed stripes to be able to send them to the host or to the storage pool. And then as we have to evict some of those, we'll compress them first, and we keep them in a DRAM in a compressed form. And as that overflows and needs to be evicted, then we spill that over into the SSD capacity. So it's a pretty interesting design, and that assists tremendously with the read performance. Next slide. That's a slightly different perspective at the same thing, but essentially it's the interaction between the caches. We can broadly call them L1, L2, L3. I mean, it's not the same thing, I realize that, but fundamentally, DRAM we can look at as the fastest medium that we have for keeping data. And then random writes go to write back mirrored SSD, and they stay there. Eventually, they background copied into the pool. Large writes go directly into the pool. Some of the stripes go into spillover accelerator and kept in compressed or uncompressed format. Here's an interesting point that I'd like to make as well. It doesn't matter to us whether the stripe is compressed or not. Okay? We realize that some workloads, particularly in multi-protocol environments, particularly in environments with file systems that store a lot of media, which is definitely non-compressible, we are OK with compressible and uncompressible data. So this architecture was actually initially designed without compression, and then compression was added on. So we were seeing a pretty good performance even without any compression. With compression, we just hit another level of performance. Next slide. So let's just talk a little bit about the caching. And what's interesting is that, as you can see, with so many different caches, so many different mediums to store data. I mean, you can look at the DRAM cache as one medium. DRAM compressed cache is another. SSD for write back is a third. And then SSD for spillover is the fourth. So traditional caching algorithms sometimes don't work for them. Just give you, I can go deep into that. Should I go deep into that? I mean, are you interested in that information? Yeah. OK, so just checking, So essentially, what happens? Let's say you have a linear scan. Let's say you have a workload that has a linear scan, and you have 12 gigabytes that you need to scan, and you have only 10 gigabyte cache. All right. So what's going to happen? How much of that workload you're going to cache, really, with typical L2ARC type of algorithms? The answer is actually none, because what's going to happen by the time you get to 11th gigabyte, you start evicting from the beginning, because that's the most, the latest one, the least recent one. Okay, and then by the time you get to the end of that cache, you haven't cached anything. So you have 10 gigabytes cache, 12 gigabyte workload is complete miss. Okay, so there's some way, there needs to be some way to deal with that, obviously, because it's wrong. So one way to deal with that is what we call, and this is just an example because there's more to this than just this picture, but fundamentally we keep the data that we cache in what we call buckets. And the buckets are simply containers that allow us to maintain data based on the number of hits. So essentially the number you see over there is essentially how many times we've seen that particular data hit. All right. So as we see more and more hits, then obviously we would progress the data inside that type of structure. There's obviously a ground floor, which is the 0, where the stripe first enters. And what we also like to work with is what we call interreference time. So interreference time is when was this particular segment of data last referred. And we're talking not about just the time, like a real physical time, but we're talking about cache time, meaning every time there's a cache access, you bump that counter by 1. You essentially increment it by 1. All right. So when we see who to evict from the structure, is we try and compare whether or not interreference time is better or worse than the one that's already in the cache. Now, if interreference time is not, is actually better, meaning that it's smaller, then we send the data directly to the bucket that it had been at one point in time. And what that means is that it might have been evicted, and it got evicted into that historical bucket where there's no more data. But then we're all of a sudden seeing the hit on it again. So we'll return it directly to the bucket that it belongs, that it ever reached. That way we're recovering from sort of evicting the wrong data. And that would serve exactly the problem with linear scans, right? So this is an example that essentially shows what happens if you have the size of cache 4 and interreference time 5, which is exactly what would happen if you have workload that's slightly larger. So this is one of the examples of the algorithms innovation that we have at Starboard. There's more innovation in that area as well. Next slide. So Tom mentioned in the beginning that what we we're able to do with this architecture is implement considerable number of virtualization features that are sometimes bolt on, quite frankly, in many architectures. This architecture was designed with these features in mind, such as, for example, snapshots and clones. So the fact that we're always doing transactional writes and we're always writing to the new stripe when we do a write very easily enables snapshots, because we never overwrite the original data. So all we need to do is throw a reference counter to the original data, and every time we create another reference, bump it by 1. By the time it goes down to 0, we free it up. It's just that simple. So that way, when we duplicate the volume map, which is essentially a linear set of pointers to stripes, we can just duplicate that, bump the reference counters, and we're good. Essentially at that point, we've created a snapshot. We haven't moved a single byte of data. We haven't pre-allocated anything. It's just a simple operation. Most of it occurs in memory, as a matter of fact. And snapshots, by the way, are immediately writable. Because they're the same as volume. I mean, they're just referencing the same stripes. If we need to write to that, we'll just write to a new area, and that creates another stripe. And that way, that reference counter changes appropriately, and we have a reference to the new stripe. So snapshots and clones are the same as volumes. We force some of the snapshots to be read-only, but really they can be written at any point in time. And what another important thing is that they are not tied to their parents at all. So as soon as they were created and they're pointing to the same stripes, at that point they become two completely separate volumes.
So do you have an integration with the upper software layers like VMware?
Yeah, VSS.
VSS, yeah.
Only VSS?
At this point, it's VSS. There is API that we can continue to integrate, but not much in terms of integration with VMware other than VAI, and I'm going to get into that. Next slide. Yeah, this is just an illustration of what I just mentioned. So volume map is a linear map of pointers. They point to original stripe. Once you create a snapshot, it points to the same stripes. New data stripes, new writes to the volume go to the new stripes. And similarly, when we create what we call a clone, meaning writable snapshot, then pointers go and point to the new stripe in both volume maps of the original volumes and the snapshot or the clone. Another interesting feature is asynchronous replication. This is something that we also designed in from the get-go into the architecture, because we know people like to replicate their data for safekeeping somewhere else, DR, and things like that. So it's snapshot-based. It's asynchronous. We essentially, what that does for us, it allows us to replicate just the data that changed. And what we also get the benefit of is the fact that when we take a snapshot, right, we're duplicating the volume map. So essentially, we're duplicating a relatively small piece of metadata with pointers. So how do we know which part changed? Well, we should just compare the pointers. If the pointers are the same, definitely the data didn't change, so we don't have to look into it. If there's a new pointer, right, it's different, then we go look at the data and actually determine what part of that data changed. We sort of wrap that up, bundle it up, and send it to DR system, to another system that will sort of unwrap it and apply to the volume on that side. All updates are bundled and transferred as compressed files. And we don't have to stick with any particular method, such as iSCSI for this type of replication. We can go rsync, we can go FTP, we can go snail mail if we wanted to with USB sticks and pigeons. It doesn't really matter. Next slide, please.
What's the RTO for pigeons?
What's interesting is when you look at the RTO, you really have to look at what capacity you're transferring. So RTO may not be that great, but the bandwidth is phenomenal.
Seriously though, what is your RPO on this?
Well, the RPO is as quick as you can actually take the snapshots and replicate. So typically it would be 15 to 30 minutes. But
Is this just an array snapshot? So I'm getting just crash consistent snapshots on my machines?
A snapshot could be crash consistent, or yes, they are crash consistent to answer your question, but they can also be application consistent with VSS. So we support both. We can have multiple snapshots taken at the same time, exactly, so that we don't miss particular I/O. Okay.
But since you run VMware, they'll be crash consistent.
That's correct, unless we integrate with VSS that runs on the guest. which we can.
Yeah, but if there's multiple guests in a single data store, you don't have time to coordinate it.
That would be correct.
So you don't have like a consistency group, is what you're saying.
Yeah, but essentially it's a consistency group. We still can do consistency group across.
Yeah,
I
you
mean,
can still do consistency groups. The problem is that if you've got multiple guests in a single data store, the VSS doesn't have a large enough time window to allow them all to quiesce before you can take a snapshot.
Okay.
There's
Yeah,
only
but
there's
how-
like a 5-second limit.
Howard, that becomes an administrative task. So you can still integrate with VSS. You just have to make sure that it happens at different times, which is solvable.
Yeah.
But you're right. I mean, if you schedule them 5 seconds apart, it's a problem. Next slide, please. So this is just a picture that shows how this replication is occurring. So there's a source volume. We have a snapshot of it. We have another snapshot of it. We compare the stripe maps. We quickly determine which parts could be different. Then we actually go look at them, determine what is different. We bundle compress it, send it across whatever connection we have, and then reapply it on the target side. Same thing can happen directly inside the system as well. Next slide. So let's talk a little bit about VEI, since that came up as well. So we support VEI. We support, the biggest thing that I think VEI is offering is extended copy. What that does is essentially telling us that we're about to copy the data from this part of the volume to that part of the volume. Okay, but what the great thing that I guess VMware gods did for us is that they allowed us to specify alignment, which means that we can tell VMware, advise VMware as far as where what are the increments and what are the boundaries at which they should run this extended copy. And guess what? We're using stripe as that boundary and the stripe size as that increment. And we report that to VMware, and VMware is nice enough to send us extended copy command that is just on the boundary and includes just, and size-wise is just exactly the size of the stripe. And that allows us to simply switch the pointer, much like we do with snapshots. It's the same thing. Instead of actually copying the data and taking data from one part and putting it on another one, we can, if this is on the same layout, then we can just simply switch the pointer and again adjust the reference counters, and we're done. So it's a very fast copy. And that is the operation that is used constantly by admins everywhere. Cloning virtual machines is a typical operation today. VDI, I don't have to tell you that. So
the benefit there is to clone a virtual machine, it's a zero copy.
yeah, it's effectively a zero copy. So same thing with write same. That's trivial. There's like 4 different ways you can specify the volume in VMware, eager 0 or not. We do all of them, and we do all of them the same. Essentially we just remap the pointers to 0 stripes. And then of course there's hardware assisted locking, which is ATS command, and that's also something that we support. Next slide.
Since you show the integration with VMware, about the replication, are you thinking about integrating with Site Recovery Manager, offering Site Recovery Adapter?
Yes, this is a roadmap item.
Okay.
Definitely.
You don't have it at the moment?
We don't have it at the moment. System RAS, reliability, availability, serviceability, essentially we're talking about here. So let's talk a little bit about again, the data integrity. Going back to the fact that we're copying the data, not copying, but rather writing always to the new stripe. That is a fundamental design decision. It helps us ensure that there's no hidden effect of partially writing the stripe. So we don't have that problem by design. Of course, the acknowledgements and all these things are protected from a sudden failure. And in fact, we don't have a system shutdown concept. We just unplug it, essentially, or we turn it off. So that is how, and if this is in a high availability environment, then it becomes a failover. So the entire system comes up on the what I would call passive node, and it's actually active passive architecture. So we do have the second node running, ready to pick up the services. All it does, it simply comes up. Parity protection for data extends within the stripe. The type of protection, as I mentioned earlier, could be selectable. And write-back accelerator that absorbs initial random small writes is protected by mirroring. Another thing about metadata. Metadata is fundamentally sitting in memory, and it is manipulated mostly in memory. The changes to that are flushed or kind of journaled to the SSD, of course, because we have to keep it on power failure. We're trying where we can to work with circular writes so that we're assisting the SSD in allocation process. But what's also interesting that the metadata we have and what it really is just a volume map, claim vector, which is reference counter for stripes, sheet map, which is extent map, and that shows us how the disks are mapped into particular layouts. All of them have checksums, and they also have transactional protection, and it's logically redundant. In other words, we built in excess data so that we can always restore if we lose part of the metadata. Let's say we lose the metadata that is sitting on SSD. For that matter, we lose the SSD completely. We at least are able to recover the entire pool, and we're able to recover all snapshots. So we're going to be as good as the snapshots, even if we lose the entire metadata along with the data on SSDs. Similarly, if we happen to lose data, because part of that is obviously written to the physical disk. So if we lose that information, or if that information becomes somewhat corrupt for whatever reason, then we can also match it with the information that's on SSD. And in fact, we do that during bring up of the system. We actually validate that the metadata is still correct. So to that extent, it adds to reliability a lot. Next slide, please. Availability-wise, so we picked the architecture that you're probably all familiar with. It's Storage Breach Bay. It's two systems in one. One is active, the other one is passive, as I mentioned. We have what that system does for us. It provides us the ability to fence another system. In other words, shut it down, turn it off, as a matter of fact. That's what the fencing does, using IPMI commands. It's very convenient because if we have to failover, it's very easy for us to trigger a failover. Surviving system will recover the cache mapping, will validate the metadata, and come up and continue on. There's physical element redundancies in this architecture. It's definitely dual-pathed hard disks. It's the multiple SSDs, JBOD enclosures that are all dual-pathed. There's dual SAS connection to all of them. And certainly, SBB form factor is an ideal fit for us because it looks like a single unit, even though it's just two systems inside. But it's not, by any stretch of imagination, we're not limited to this particular hardware implementation. Because we could just take two systems. And this is what the architecture is fundamentally different from a lot of others, is that we can take two systems. We don't have to connect them with some mighty 10 gigabit link or whatever, or SAS or whatever. We can just take two systems, connect them to the same JBODs using a switch. It could be LSI switch. It could be just a dual-pathed connection. And that's enough. It's going to be a highly available system. Or for that matter, we can just have a single node. And that will run this same exact architecture without redundancy. And some markets are very open to that as well.
Yeah, there are definitely some advantages to using a shared SSD as the right cache.
Correct.
And not having to maintain coherency between the two controllers.
Exactly.
It solves a lot of problems.
It solves a lot of, it just simplifies. It makes this, a child play. It really makes it simple to implement. And another interesting point to that, Howard, is that they are coming out with PCIe connectable SSDs. So there's absolutely no reason why we couldn't have dual connected 2.5-inch SSD connected to both nodes, and that will eventually, essentially, solve the SAS limitation that we might have. Even though with 12 gigs, it's not such a limitation anymore.
Yep.
Next slide, please. So yeah, this is just an illustration of what I mentioned. So that's the active and standby controller connected using passive backplane, and all there is really SSDs and the hard disks. And of course, the controllers are the network controllers or fiber channel controllers. They're similar in each canister, and they take over and hijack the IP and all that good stuff with high availability. Next slide. So yeah, I mean, this is a slide about data availability from the pool. So how do we deal with some of the errors that we obviously see occurring? So drive failures, especially when you have a 3 terabyte drive, that's a lot of data. I mean, you have to think for some time before you really fail that. We just make decision to fail it because it could be completely full with data, and you will need to recover all that information or rebuild it somewhere else. right? So what we do is for read failures, we try our best to restore the data on the fly. So we would encounter the error. We obviously fix it using parity, but what we also initiate at that same time is write to that stripe in hopes that the disk, which is smart enough, to hopefully just redirect it to another sector, or maybe even overwrite the existing sector and fix that ECC problem that is there. And in many cases, that is sufficient. When it's a write failure, well, maybe somebody just pulled the hard disk out, right? Or maybe somebody, maybe we lost a connection on the SAS bus or something like that, intermittently. We're not necessarily failing the entire disk. What we do, we fail a microdisk. We fail the extent. We fail the extent that we tried to write to, and we immediately divert the write to other extents. We essentially take this particular disk out of consideration for pre-allocated stripes. And then if it comes back, which it might, and it does, a typical demo would be you pull the disk and continues to write, and you put it back in, it comes back, and it recovers automatically. So we just need to rebuild the extents that had been written at the time of failure. It's usually 1 or 2 extents. So it's a lot faster to rebuild 1 gigabyte than rebuild 3 terabytes, right? So it's about 3,000 times faster. So the other consideration is what happens when the drive finally fails. I mean, it does, from time to time. So it's a permanent failure. We know that it doesn't come back anymore. So what we do, remember, we have spares embedded into every stripe. So what happens is we start using that spare to rebuild the data. Now, if you think about it, the rebuild is occurring not to just one spare that is pre-allocated for it, but it's occurring across the entire pool. So it's almost happening in parallel, much like Hadoop recovers. It recovers across the entire pool. The more drives you have in the pool, the faster the recovery is going to be. So that assists recovery tremendously.
Can one drive be a spare for multiple stripes?
It actually is, if you think about it. All drives are spare for all stripes, fundamentally.
Yeah, there aren't spare drives, there's just spare space.
Yeah, it's just a spare.
I see what you mean. Okay, sorry. Right.
But it's completely, it's completely uniform. So in other words, one drive could hold spares for multiple layouts.
Yeah.
So
the other advantage is if you have a spare drive, that spindle isn't adding its IOPS to the active pool. It's just sitting there waiting to be used. If you have spare space, you increase the available backend IOPS.
All drives participate in storing data, and all drives participate in providing spare space.
that's a great point. Thank you. And then, of course, background layout scrubbing. Again, we introduce a task which when the system is somewhat available, it goes in and tries to revalidate all the parity across the entire pool and make sure that all the pool is readable. And if it's not, then it fixes it in place. So that way we can catch the problem much earlier. Because what often happens is that there's a huge capacity, but the active data is relatively small. So this huge capacity goes sort of unaccessed for a very long time. And during that time, it actually may lose the ability to be read. So that ECC error suddenly grows larger than what the software can fix. And unless you have this background task that runs periodically, you will never know about it. You may not know about it for months until you finally access that particular stripe and it's no longer readable. One sector of it may no longer be readable and it's already a problem. So that helps tremendously. Next slide. As far as serviceability, you've seen the dashboard, so there are some health indicators on the dashboard. Normally it's just a check mark that everything's okay. But if we're running out of capacity, if there is a layout, a health issue, and what that means is that we have some failed drives in a layout, which means essentially that we have partial failure of the pool or degradation of the pool. And it could be displayed as a percentage as well, because this is kind of informs the admin this is how much data potentially at risk. And then we have hardware views that assist with identification of a particular device that failed. That needs to be, like, for example, if there's power supply failure, then the UI will show which particular power supply is missing or at failure, and so on. We do proactive maintenance actions. Of course, we monitor everything that could potentially happen with the system. Again, this whole point is that to make the life of the system admin easier. Give them enough notification, enough time so that they can react if anything is wrong with the system. Perform scrubbing, data integrity checking and healing. Certain statistics on traffic cache disk utilization, and basics on CPU and memory as well. We periodically generate reports and as email. I mean, this is all typical stuff. I think that's it. And thank you for your attention. And if you have any questions, let me know.
So questions, curiosities, did we go through that too fast? Probably went through that too fast. But,
Not for this year.
So replication is asynchronous?
Correct.
Because it's based on snapshots?
Correct.
Is there a future upgrade on the roadmap that you will make it synchronous as well?
Yes, we're certainly thinking about that, and that would be as simple as adding DRBG to that architecture. Completely lends itself. I mean, this is a well-proven architecture out there, and it's something that we were thinking about.
Okay.
So, but when do you add data deduplication?
Say it again.
When do you add dedupe?
Okay, that's a great question. Well, there's a couple things there that you probably were able to glean from this. That there's like, first of all, there's a concept of no dupe, right? Especially when we're doing extended copy. You know, rather than catching it on the inline deduplication, we're just not duplicating the data to begin with. Same with the snapshots and so on and so forth. But I can tell you, dedupe is very much on the roadmap. You know, because certain things we cannot catch. You know, with this, and certain things are not as nice as VAI and not as proactive. So for those instances, you know, a great example would be copying gestures database, right? I mean, so it performs a copy at ideal point at which you can perform a dedupe, right? Or any kind of a large file copy that may occur. So this is something that we can do while the data is still in a Stripe cache, and it's squarely on the roadmap.
So you guys are local here to Colorado, is that right?
We're local here to Colorado, and we're also local to New Jersey.
To New Jersey?
Yeah, we're split in 2 locations.
Where did it start?
In New Jersey.
In New Jersey.
Parsippany.
Does that explain the Starboard name?
No.
I can't figure out why a storage company in Colorado would call themselves Starboard. So
Because Bill likes to sail.
Here?
So starboard is the right side of the boat. A boat on starboard tack has the right of way, so starboard's the right storage.
Gotcha. I like to sail, so I was curious.
And it's a little bit of a play too on the previous company.
Which was left hand,
Ah,
which would be port.
I just figured it was that.
Right.
I didn't think it was
that's funny.
Question, right now you use solid state for caching and use spindles for the run. Does the roadmap include going on SSDs or?
Not at the moment. So we are actually believing in hybrid. I mean, this is the whole point. We believe that a hybrid architecture is essentially something that, to Tom's point, something that everybody should use. But you can look at it in a different light. For example, you know, there's definitely TLC devices coming out and so on. So not all SSDs are made alike. So if we have hybrid stack, then we can just as well integrate lower performing type of devices at the lower, you know, much like the pool is, so that I can envision the pool made out of TLC, for example. Yeah. But I don't think TLC is there yet to be able to get that done.
But that's a great question. If you get to the point where you want to store a bunch of, if you will, cold data that's not going to be read or written to a lot, yeah, then you've got a tier that's made up of TLC potentially. The same thing would apply. Maybe the benefits of the caching go away, but the benefits of the dynamic disk pool could be applied to an all-flash scenario. We haven't done it yet, to Karel's point, just because we feel like, frankly, that's a small market, and we're after a much, much bigger part of the pie, and hybrid addresses a much, much bigger part of the market right now than all-flash. Could we do it? Yeah. In fact, we'd probably end up throwing away or not making use of some of the technology that we've got in order to accommodate all-flash. So, yeah.
Thank you.
Yep.
All right.
Is there an SRA adapter for your replication?
No, not at the moment. Would like to have that done, so that is on the roadmap. Some of that integration is on the roadmap, because there's no reason why it couldn't be done with this.
No.
All right.
Other curiosities, questions?
Well, maybe that's, you said you wanted to reduce user interaction as much as possible.
Yes.
Hence, all the decision the system makes itself. But why still ask the user to create a volume and decide whether or not to be a mirrored stripe set or a rate combination?
That's actually a great question. There are certain things that we cannot answer ourselves unless we're actually watching the traffic and everything else. But there's some advisory that the user can give us. And that advisory comes in form of selection of the basic layout that they'd like to have. And in some cases, they actually want to have that control. They want to know that this is sitting on 15K drives as opposed to 7200 drives, right? So it's a minimal amount. This is at least we can do that. The least we can do for the users. And typically they're very open to that. We also have some recommendations as far as what's best to choose for what application, and we cannot know a priori up front, what application they're going to put on it. So that gives us the chance to ask the user for what is it that you're trying to do with our system, with this particular LUN, by the way, because you can have multiple of them, going to the same storage, and that gives us a chance to ask the user to specify what is that going to end up being.
Okay. So if the user decided to make it a mirrored set, could he change it into a rate set later on? Or is that fixed?
No, that is fixed at the moment. So that is fixed. However, you can always migrate.
Yeah, you have to migrate.
And there's migration tools available that will help with that.
Okay.
For storage with motion.
Or that's a migration. That's a great migration tool.
Yeah, I'll comment on your question, maybe build on it a little bit in terms of user control. One of the questions we get asked, not so much from the customer so much, but from a lot of analysts sometimes is, well, can you guarantee the quality of service in terms of performance for a particular volume? And we tell them not necessarily, because we've got our performance elements, if you will, allocated to address the performance needs of the whole system. And we're making intelligent choices among all of the workloads out there on how to use that SSD. If we wanted to guarantee it 100%, well, now we've got to essentially pin that volume to the SSD, okay? Yeah. We're going that route, and maybe we'll allow the user to do that. We don't think they're going to take much advantage of it, because now they've just, if you will, crippled the opportunity for their other workloads to take advantage of the SSD. They've done what we call fat provision, their performance requirements, and that's a step backwards that we think. But you know what? There's some people that want to do it, so we'll probably make that available to them.
Thank you. There's still another question, though. There is a single dynamic pool, and all the spindles will automatically be added to that pool, but I can think of a couple of customers that want a pool separated for a specific purpose. Is that an option as well, that you can still create two pools in which you add the volumes?
So let me ask you, why would you do that?
Well, I asked customers as well, because if you have a new application of which you don't know the I/O profile yet, you want it in a test environment, but the size of the application that's going to run isn't always available in a testing environment, so they want to isolate it before putting it into production, and isolate it in such a way that it will not influence the rest that is already in production.
Right. So there's at least one way that you can use for that. What you do, you put a different storage class for that. That will essentially carve out a pool, sub-pool for you. But the reason I asked that question is because this is not something that we recommend. We actually recommend to keep workloads on the entire pool. It is our responsibility as a software stack to make sure that the I/O blender effect is significantly reduced, so that this problem does not even come up. And the whole idea of flash mostly design of the hybrid storage system is to perform exactly that, isolate. So the lower tier, the pool, is really capacity tier. It's not a performance tier by any stretch of imagination. It's designed to store the data that is not on the SSD. And everything else is handled by the SSD. That's why you have two different types of accelerators. You have the write accelerator for writes, read accelerator for reads. They're not the same. They have different type of access profile, very different type of access profiles, and that's what provides the performance at the end of the day. So if the system senses that we're running out of that capacity on the SSD, it will inform the user, and they will just add the SSD at that point. And then, of course, if they want to grow capacity, they will keep growing capacity. And to Tom's point about QoS, I mean, adding QoS is essentially trivial to this design, because you would start controlling how much capacity or how much space you allocate in DRAM, in read and write cache for a particular workload. So this is a logical step forward here.
just a more expensive step for the user to do that.
Right.
Yeah.